So chapter 1 in the calculus-based physics talks about vectors, and in the college physics they don't talk about vectors really until about chapter 3. But so since it's in chapter 1, I'm going to go ahead and introduce it for you for the calculus-based students, and when we get to chapter 3 you'll already had some of it. So it's section 1.7, vectors, vector addition, and there's I think there's a couple of sections, components of vectors, unit vectors, products of vectors. I think that's it. Okay, so this is kind of an introduction to vectors. So we talked, well, I may not have talked about it in class, but in physics, a quantity can be two types. It can be a scalar, which is things like temperature, voltage, mass, time. Those are all scalars. They just have a value in units. A vector, on the other hand, has both a magnitude, a value, and a direction. And we represent vectors as arrows. So if we have, this is an example of a vector. It's got a tip and a tail. And if the vector we're talking, let's use displacement as a vector description. If we start at this point in space and we end up at this point in space after a certain amount of time, the displacement from here to here can be represented by this vector. The direction shown by its orientation relative to, say, a coordinate system that you might have placed here. So let's just go ahead and put a coordinate system in there that matches up where the origin is the initial starting point. And it doesn't always have to start here, but a lot of times vectors we do show relative to the origin of a coordinate system. So the question is, how do you specify the information that's in a vector? So typically well, let's start off. So let's terminology. If this is a vector A, we typically use a capital letter to represent vectors, and we have an arrow over top of it which shows that it's a vector. Now, the value of the vector is its length from the origin or from its one side to the other. So it's just the straight distance length from here to here. So let's say the magnitude, we represent that by using these like an absolute value sign. So it's two vertical lines. So if this is the vector A, this is the magnitude of the vector A. And this is a scalar. It's just the length, it's the number, meters, whatever the vector represents. Sometimes vectors represent distance, sometimes meters per second, meters per second squared, newtons, momentum, lots of different things. Now, it doesn't matter how we get from point A to point B here. We can go this way, we go around that way. The key thing is that we start here and we end up there. So that's a vector. So it's with certain, the path is independent, basically what I'm saying there. Okay, now, as far as the direction, in general, we measure the direction relative to some coordinate axis. So in this case, because we usually deal with the x-axis, go back to pre-calculus, we usually measure the angle with respect to the positive x-axis. Now, you can show visually, you could use another axis as the angle, which I'll demonstrate in a second. For right now, let's say the vector is going to the right and up. So the direction would be specified by theta, and I'll say we don't normally write this out, but relative to positive x-axis. We don't write this out because usually there's a drawing that tells us this or demonstrates what that is. So you get a magnitude and direction. Again, the direction is an angle in radians, or it could be in degrees, I guess. You just have to be careful. Yeah, it could be angle in degrees. Okay, now let's say we have another vector. Here's the coordinate system. starts at the origin, goes this way. So there's probably two ways you could do this. You could define the, well, three ways really. It would make sense. You could define the angle from here to the vertical axis. Let's call that alpha. We could define it relative to the horizontal axis. It's beta. Or we could do it relative to the positive x-axis. I'll call that theta. So any one of those angles could represent the direction. You just have to know, either from a drawing or from writing it out explicitly, what the angle is with respect to. So a lot of times we actually use one of these two relative to one of the near coordinate axes. Usually you don't use it all the way from the positive x-axis, even though that may make no sense. Again, the magnitude would be the length of the vector. Okay, what's next? Now, let's say you have a vector A that is as such. So here's vector A. Again, it would be, the magnitude would be the length, the angle would be probably relative, in this case, to the positive x-axis. So the question is, what is negative A? Do you have a negative sign? What does that do? Well, what happens with negative A is the magnitude is the same. So the length is the same. But what you do, so let me just clone this thing. So there's the same vector. What you do is you take the arrow and you move it from one side to the other. So basically the sign of the vector is the direction relative to the original vector. So this would be vector A, and this would be negative vector A. And you can see if well, we'll have to talk about adding vectors here in just a second. So at the same length, they just have the top 180 degree or pi radians different angle. Let's see what else is in here. And typically, if you're doing things graphically, you'd have to include some kind of units in here. So normally you would think the units would be distance, but they could be, these vectors could represent velocity, which has units of meters per second, or acceleration, which is meters per second squared. And so you'd have to have some kind of scale factor. You have to have some scale if all you were doing was doing everything graphically. You know, this is equals 1 meter per second is this distance. And then you could use the scale to determine what the length of the vector represents when the units are not dimensional units. Okay, so that is just some vector stuff. The next thing is adding and subtracting vectors. So the first thing we're going to do is we're just going to talk about it in a graphic sense. Once we get to doing components of vectors, which is the next section, then we'll do it according to the components of the vectors. But for right now, we're just doing everything graphically. So what I'm going to do is I'm going to show two vectors. And the reality is the vectors, where the vectors are, doesn't matter. What matters is its length and its direction relative to an axis. So I've just got two vectors here, and this red vector is the same no matter where I have the vector. A lot of times we will put the two vectors from the origin, kind of put them on an equal basis, but that's just for convenience. So I might put a vector here, and I might put a vector, put the same vector down here. What that does is it, makes it more obvious what the direction of the vector is, because we can use this coordinate system and the angle between the vector and the coordinate system to determine the direction. But the reality is this vector doesn't change depending upon where it is in this coordinate system. Okay, so how do you add vectors? Well, you might think, oh, I just add the, here's a wrong example. Let's say vector A is a vector which is 10 units long So that's the magnitude at 30 degrees, and vector B, that's a vector which is 5 units long at 60 degrees. Like that. So is the answer 15 units at 90 degrees? No. Okay. The actual way you do it is you take one vector, and it doesn't matter, just like addition, you don't need to know, it doesn't matter what order you add the two vectors together, you're going to get the same resulting vector. And the vector you get is what's called the resultant vector. So the resultant vector, I'm going to use R to represent that, we would show that mathematically or symbolically as vector R is going to be vector A plus vector B. So let's make the red one A and the black one B. So what you do is you take the first vector, put it at the origin, take the second vector, put the tail of the second vector with the tip of the first vector. And then the resultant vector goes from the tail of the first to the tip of the second. So that's the resultant vector. So this would be vector C, and this would be vector A, and this would be vector B. So A plus B is done graphically as such. And I'll leave C there just to show if we take B plus A, we get the same resultant vector. So it doesn't matter. So we can just say order's not important. In addition, it's just like algebraically. And if you have three vectors, then you do the same thing. So let's go ahead and look at an example of how you would add three vectors graphically. So I'm going to use, okay, so there's one vector, there's a second vector, there, third vector, let's go that way, put a little arrow on it. I've got to group those two together so it stays as a vector. Okay, so those are the three vectors. So if you add these three vectors together, actually that's not a vector because it has two arrows to it. So again, I just picked the wrong thing. So there's vector A. So A plus B to the tail plus C. So the resulting vector, the resultant vector is that, from the origin to the end of that. And again, if I do it in a different order, if I take B plus C, or you can see that order works. If I do this one, so I go from here to here, and then I do this one back this way, I get into the same point. So it doesn't matter how many vectors you have. The order is not important. And the resultant vector is from the tip of the first vector to the tail of the last one. And so the tip is the side. If you think about an arrow, it usually has little quills on here, and then you have the arrowhead. We don't show the quills, but you do have the arrowhead. So that's the tip of the arrow. That's the tail of the arrow. Okay, so how do you subtract vector? Let's say we'll have a resultant vector, which is vector A minus vector B. So what that is it's going to be vector A plus the additive inverse of vector B. So I just put the negative inside of parentheses. So what this does is changes from a subtraction problem to an addition problem. But I do have to change the direction of vector B. So what I'm going to do is I'm going to draw vector A and vector B, not negative vector B, but vector B. So let's say this is vector A, and this is vector B. So how do you subtract vector B from vector A? What you do is you take vector B, which I'm going to say is the red one here, and then we're going to flip the arrow heads tip is going to switch with the tail. So this now is minus, so B was from here to here, negative B is from there to there. So let's clone this thing. Clone. Okay, so and let's make that so it's the other way around, the way we started. Okay, so that was, I'll move that. So that was, that's vector A. So let's write that down. Vector A. This is vector B. This is negative vector B. So B, it's vector B with go in the opposite direction. So A minus B, let me group those two together. A minus B is A plus the negative of B. And therefore the A minus B is this vector. So the blue vector is, this one here is vector A minus vector B, which we did as vector A plus the negative of vector B. I think that's pretty much the gist of it. Oh, there's the third case, yeah, multiplying by scalar. So if you have vector A like this, what is two? So if A, this is vector A, what is 2 times vector A? So the scalar 2 does not affect the direction, it just affects the magnitude. So in this case, that's A. Let me just clone this thing so I can get the distance. So there's A. So if I have A plus A, then this would be 2A. So I could take that out of there. So this vector here would be 2A. So anytime you multiply a vector by a scalar, you're just changing the length of the vector. You're not changing the direction of the vector. Okay, so we're going to stop there. The next thing we'll talk about is components of vectors.